Creo que los conocemos a todos. Ignacio.
Los speakers tienen hasta ahí.
Sí, sí, así ya estás arriba. Bueno.
Okay, so I think we can start with the second session. So we will start with Patricio Moreno from the Universidad de Andrés. He will talk about multi-domain information control of marine aerial robots. So we will have 15 minutes and then 5 minutes for questions. Thank you.
Thank you for the presentation. I'm going to present this work, which is done with Leonardo Garberoglio from the Universidad Tecnológica Nacional, la Facultad Regional de San Nicolas, and Ignacio and Juan Giribet, also from Universidad de San Andrés and CONICET. The outline of this presentation is the following. I'm going to present a brief motivation on why we are presenting this work, on how we see that this is useful for the wave energy workshop, an introduction on unmanned vehicles, and a brief introduction also into multi-robot coordination and control, some results and conclusions and future work. Our initial motivation is due to environmental monitoring, where acquisition, administration, and making available the data from environmental monitoring is key for a greener and sustainable future, as we have been talking today. And this has been shown by the National Oceanic and Atmospheric Administration from the United States. And there has also been some work on how to on mobile robots teams to perform this task in some sort of autonomous way. And this is where we have been focusing our work. But this is not the only aspect that has to be considered when we talk about sustainable futures. And we also have to think about how the energy is produced. That is the theme of this workshop. And we know that there have already been operational multiple wind farms, and there are planned and projects for some other types of energy converters. This workshop is a proof of that. Particularly in this case, the wave energy converters. And as yesterday Professor Ringwood said, The maintenance of this type of systems is not easy. It's a long, continuous, and stressful task. But we think that it can be performed in an autonomous way, or mostly in an autonomous way using autonomous mobile robots. We have it is common in the area to use in environmental monitoring, at least, to use UAVs to perform monitoring tasks. For example, UAVs that have cameras and can perform the monitoring task and the inspections, and autonomous surface vehicles that can do or are good tools for in situ sampling of the data. So today there were shown works where they had to do some sort of environmental assessment before the installation of the energy converters, and we have seen that this was performed manually. This can be done in an autonomous way, but this can also be these vehicles can also be used to perform the inspection and the maintenance of this type of systems. Partly because, or how we can use them together. We know that unmanned vehicles have limited payload capacities and constrained operational times, mostly under an hour. And if you have to go to an offshore installment, under an hour is really a short period of time. But they have a great maneuverability and a broad perception of the environment, which are good features to perform this the inspection and tasks. And we have autonomous surface vehicles, the ASVs, that have high payload capacities and long operational times, which are good aspects to perform the offshore task that we are proposing. But they have a limited perception of the environment. So if we think of the synergy that is between these type of vehicles, we can think on collaboration tasks between these type of vehicles to take the best part of both type of vehicles. So we can have a system that has great maneuverability and broad perception of the environment and long operational times. If we can build a system that use both of these vehicles. But to work with this type of vehicles, we have to think in controlling the formation of UAVs. The typical formation of, I also come from the robotics and control area, as many of the speakers that have talked here. But I wanted to emphasize the most common, or some of the most common techniques that are in the area. Leader-follower controlling strategy, when one defines a leader robot and the others follow with predefined parameters. The swarm robotics, where we have a lot of vehicles, thousands of vehicles or hundreds of vehicles, and simple rules between them, which are going to produce an emerging behavior, but we can control exactly where these vehicles are going to be. So these swarming robotics are not sufficient for this type of, for the task we are proposing, where we want to know where the vehicles are. Imagine that we can't go to a wind turbine with something that is, well, more or less near the turbine. We have to know exactly where it is. And then the cluster space control, that is the technique that I'm going to present here, where we define some variables with respect to the task that we want to perform, and it can be seen here, but these vehicles form a triangle, and we can consider that this the triangle is the thing that we want to control, not the vehicles, but the cluster. So, for example, we have the very center of the triangle. Imagine that we have a load there, and we want to transport that load. We are interested in how we are going to transport it, and not how the vehicles are going to move. We want the movement of the vehicles to be something that is controlled internally. So for each cluster, for each task that we are going to define, we need to specify a cluster space definition, a cluster state variables. So for example, in this case, where we have an ASV and a UAV, we have 7 degrees of freedom, so we have to define 7 variables. And particularly, I wanted to emphasize the swath parameter here, that is the area that we are going to cover with the camera. We are not going to control explicitly the heights of the UAV, but this is related, obviously, with the swath area of the camera. So this is a common control loop. We have the cluster that it's defined using the ASV and the UAV. We measure the parameters, the position and velocity of these vehicles. This fits the cluster kinematics equation that were the ones that were in the previous slide. And using these variables, these equations, we compute the cluster's position and velocity. This is compared with some predefined reference that the cluster has to follow. A command is produced for the formation to follow that reference, and then the cluster kinematics equations compute the commands for each vehicle, because ultimately we are controlling the vehicle, so we have to make the inputs for those vehicles. And we can also have a mission controller in case we need to control one or more vehicles manually, for example, in case of failsafe. So this is a classic control feedback loop. Now I'm going to present some simulation results first, just to show how the system works and how we work with the system. We used as our simulation environment ROS Melodic, which is a common middleware. It's not an operating system, but it's the middleware that allows us to build the communications infrastructure. And Gazebo 9, that it's the simulator, the physics simulator, and the user interface that shows us the ASV and the UAV. As an ASV model, we use the ClearPath Robotics Heron ASV, which is an available model. And as a UAV, we use the model of an Iris, which is a robot that is included in the simulator. Then, using programming in Python, we implement the controller using ROS nodes, which are the building blocks of the ROS infrastructure. And it will allow us to communicate in a subscriber-publisher fashion. Okay, here we can see some simulation results, an overview of the results. I'm trying to go a little bit faster. Here we can show that the formation follows some predefined parameters. The UAV starts on the ground, and also the ASV starts on the ground. Then they perform that square trajectory with some parameters that, for example, we see here the swath is 6 meters, and then another simulation where we change, for example, the gamma parameter, which is the orientation of the UAV. But the interesting part is the experimental task, the simulation. We use it to check that our controller is working, because the way that we use the simulation environment, once we use it in the once we validate it is working, we leave it like that and we use it directly with the vehicles. The same implementation that we were using for the simulation. Both vehicles have the same low-level controller, which is a PICSOC, which has the inner loops of to control the vehicle, so we can command each vehicle saying, I want you to move forward with this velocity, instead of controlling the way each rotor has to turn. And they also have a Raspberry Pi, which is a small computer, which has Ubuntu operating system installed, and ROS, which is going to be the framework that we use, the middleware that we use to communicate. The vehicles communicate using Mavlink, which is a communication protocol, and its implementation for ROS, which is MAROS, and everything communicates using a Wi-Fi network. We also have a ground computer, a ground station, where the cluster space controller algorithm runs. It is centralized, so we can check and we can have all the input and the fail-safe operations with us, because the computer could be on the high payload vehicle. And for this experimental setting, we have 4 weapons that is going to, where the ASP is going to move, and the cluster space parameters that are going to vary during the experiment. So this is a short video where we can see on the left someone on the coast that is filming the cluster, and we can see that the boat, the ASV and the UAV are following a predefined trajectory. It's not the full trajectory, and we can see what the UAV is seeing from using its onboard camera that it's pointing downward. Now we're going to see that the boat will turn and engage to the following phase of the square that we have seen previously. And that's all the video, more or less. Okay, thank you. And here we can see a graphic of the data that was collected using these vehicles. We can see that the ASP is performing that square trajectory, and the ASV is following from a height, a predefined height that it's defined not in terms of its height, but in terms of the area that we want to cover. And it starts on the upper part, and then on the second turn it goes down to follow the reference. Here we can see on the left side how the swath is varying, and on the upper graph we can see the reference, which is a step, and the measured parameter. And on the lower part we can see the error of that same variable, and we can see that it is following close to 0, and except when the step changes, obviously. And we can see that it follows with a relatively close to 0 error. And on the other part we can see the gamma parameter, the orientation of the vehicle, that it's varying with it's following the reference and also near 0 error. So these are 2 of the 7 parameters that were being followed. So for our conclusions, we show that, or we think that autonomous robot systems will be a key component for future WEC farm deployment and maintenance. We presented a formation of unmanned vehicles that operate in different environments in a coordinated fashion or manner to perform a specified task. And we present a cluster space controller that allows us to define parameters that are dependent on the task that we want to perform, but are more intuitive for a human operator to follow and to understand when they are seeing these results. And as a future work, we plan on replacing the cluster space PID controller that was shown here with more robust controllers, mostly we are thinking in offshore environments where we have higher winds, stronger winds, and marine currents that are going to make the boats drift. And in particularly, some model-based controllers following the work of Professor Fossen, which shows the dynamics of these marine crafts. So thank you for your attention. If you have any questions.
Thank you, Patricio. So, are there any questions? Yeah, Mauro?
Hi, thank you for your presentation. 2 quick questions. One, I understand that you have like a global like coordination algorithm between your devices, and there is some local like collision avoidance algorithm to like perform like some emergency maneuvering or something like similar.
Yes, this is not present in this presentation, but we have other works where we include some collision avoidance techniques. For example, a potential field, for example. Another where we used in other tasks where we implemented some filming. We call it chip cranes, robots that have to perform a cinematic filming task, and using what these vehicles see and what the central controller knows, we implement some optimization on how these maneuvers, these commands have to be implemented to avoid collisions.
Okay. Just the last question about like a technological one. Have you planned like some hybrid robot, so like something that goes into the water and then goes up to the air, or is like it's not feasible? It's better to divide the scope and the technologies.
No, what we are planning to do is here I showed that the UAV take off from the coast. And the ASV is small, but we are thinking in a UAV that can land on board the boat, okay, and charge its batteries there.
Okay. Thank you.
Thank you, Mauro. Other questions? Okay. Yeah, Facu.
Hi, thank you very much for your presentation. My question is regarding what kind of robot controllers are you thinking on add?
On our future work?
Yes, on your future work.
Thank you for your question. We are testing now some sliding mode controllers, some non-linear sliding mode controllers, including the model that I said for the boat, into the cluster.
Okay, thank you very much.
Demian?
I can use this one. So thanks, Patricio, for your presentation. It's very nice. I was wondering, in this case, you have a leader and then you have a follower. and the controller is implemented on the follower, I guess, no? If I understood correctly.
No. The formation is.
I mean in the experimental.
No, it's a cluster, the same cluster that we defined for the simulation, but part of the parameters are similar to what a leader-follower formation would be, because we say that the leader-follower formation is can be seen as one specific case of a cluster speed controller.
Yes, I was wondering, particularly on the stability analysis, when you have several vehicles, and you have one controller for each vehicle, do you have results for stability conditions or these kind of things? Or because I guess that it's not the same situation when you have one controller controlling the whole formation, and when you have several in a distributed
manner. I mean, do you have stability results for that, or?
Not for this case, but here we have one controller for the whole formation.
Yes. Okay.
And the inner controllers, the inner loops for each vehicle are part of the low-level controller, but those are inner loops inside. We assume that those vehicles are already stabilized.
Okay.
But the controller here it's one for the formation.
Okay.
We have not for this case, but there are works where the analysis for the stability of this controller is made.
Okay. Thanks, Patricio.
Okay. Just a quick curiosity for me. So, where is the main challenge and/or constraint? Is the cost? Is the autonomy, like the energy that you have on board, or is indeed the control?
No, the main challenge here is to build the system and to test it. The cost of building this system, and how we plan on the autonomy. The main issue using the UAVs is the autonomy, and how you can take this offshore and make the UAV perform its task and then recharge and then perform another task, thinking in a wake farm or a wind turbine farm where you have, 100 devices that you want to inspect, and you need the vehicles to work hours.
Yeah, great. So thank Patricio again.